This is the third part of the Hopfield Network. In this video, we will look at the storage capacity of the Hopfield Network, followed by a look at the pseudo-inverse learning rule. This video was produced in Korean and then translated into English. The audio was generated by AI text-to-speech. In this video, we will look at the storage capacity of the Hopfield Network. And then, let's look at the pseudo-inverse learning rule to greatly increase the storage capacity. Finally, we will implement code to store and retrieve MNIST image patterns from a Hopfield network using pseudo-inverse learning rule. Now let's look at the storage capacity of the Hopfield network. The storage capacity of a Hopfield network refers to the maximum number of patterns that can be stored and successfully recalled for a given number of neurons, n. When trained with Hebbian rule, the storage capacity of a Hopfield network is limited to approximately 0.14 n. Many studies have shown that when alpha is defined as p over n, alpha is approximately 0.14. Here, p is the number of patterns that can be successfully stored and retrieved. And n is the number of neurons in the Hopfield network. In this figure, we can see that the retrieval rate drops sharply when alpha is around 0.15. Additionally, this paper states the following about the storage capacity. More careful arguments, based on probability theory, lead to the conclusion that already for p larger than this value, the original patterns become unstable. This implies that retrieval of patterns free of errors occurs when p is less than this value. For MNIST dataset, each image pattern has 784 states, +1 or -1. So the Hopfield network also has 784 neurons n. Therefore, this Hopfield network trained with the Hebbian rule can theoretically store and retrieve about 110 image patterns. Alternatively, by this formula, this Hopfield network can theoretically store and retrieve about 59 image patterns. Next, let's implement the code to store and recall MNIST image patterns in a Hopfield network with Hebbian learning rule. Load the MNIST dataset. We will only use 2 MNIST images. The pixel values of each image pattern are between 0 and 1. Convert them to bipolar values, +1 and -1. Next, we compute the weight matrix of the Hopfield network using the Hebbian learning rule. Fill the main diagonal of the matrix with zeros. The 2 MNIST image patterns are stored in the weight matrix. Now that the weights have been determined, we can say that the Hopfield network is trained. Next, we write a function to calculate the energy using this formula. Next, we write a function that generates a corrupted image pattern. This will erase part of the bottom of the MNIST image like this. Next, we use the trained Hopfield network to reconstruct the corrupted images. When a corrupted image is fed into a Hopfield network, the original image is output. As we did in the previous video, we use the energy function to retrieve the image stored in the Hopfield network. Compute the initial energy of the corrupted image and store it in a list. This is to observe how the energy changes as the image is restored. Let's randomly select 50 neurons and update the state of each neuron. Update the state of the selected neurons one by one. Compute the energy before flipping the state of a neuron. Flip the spin of the ith neuron. Compute the energy after flipping the state of the neuron. Compute the energy difference delta E before and after flipping the state. If delta E is less than 0, the energy has decreased due to the flip, so the state is flipped. The state of this neuron has already been flipped above, so we do nothing here. If delta E is greater than 0, the energy has increased due to the flip, so the state does not flip. The state of this neuron has already been flipped above, so here we flip it back to its original state. Compute the energy of the changed image and add it to the list. Repeat this process 100 times. Visually check the reconstructed image. Let's check the results. Here are the results when storing and retrieving only 2 MNIST images, like the code on the previous page. You can see that the corrupted image has been successfully reconstructed into the original image. The energy of each image is also significantly reduced. However, if we store 3 MNIST images in the Hopfield network, we can see that it fails to retrieve them as shown in these results. The energy is reduced, but the corrupted image cannot be reconstructed. Therefore, we can say that the storage capacity of this Hopfield network is only 2. In theory, the storage capacity of a Hopfield network with 784 neurons is said to be about 110, but in this experiment, it was only 2. I'm not exactly sure why. To increase the storage capacity of the Hopfield network, various methods have been proposed, such as the pseudo-inverse learning rule and the Storky learning rule. In the next page, we will dramatically improve this capacity by using the pseudo-inverse learning rule. And in the next video, we'll improve this capacity using the Storky learning rule. Let's run this code. We got the following results. If we store 3 MNIST images in this network, as can be seen in the results, the corrupted images cannot be reconstructed. Next, let's look at the pseudo-inverse learning rule. We will use the method presented in Section B of Chapter 4 of this paper. Let X be the set of input pattern vectors of size n, and let Y be the set of target pattern vectors of size n. Then the output Wx of the Hopfield network becomes Y, where W is the weight matrix. If matrix X has an inverse, we can rewrite it as follows. If X is not a square matrix, then no exact inverse will exist. But it has been shown that it will minimize to this mean square error by using the pseudo-inverse matrix. And this can be written as follows. X superscript plus indicates the Moore-Penrose pseudo-inverse matrix of X. If the target pattern Y is the same as the input pattern X, then W becomes like this. As you know in the Hebbian learning rule, W is like this. Since X plus is a kind of inverse matrix, XX plus becomes the identity matrix. If the right pseudo-inverse of X is like this, then XX plus becomes the identity matrix. so we can write W as follows. And the pseudo-inverse of real matrix X is the unique matrix that satisfies the followings. The pseudo-inverse weight matrix can also be calculated as follows. Pseudo-inverse learning rule uses the pseudo-inverse of the pattern matrix, while Hebbian learning rule uses the pattern correlation matrix. This learning method is not incremental, which means a new pattern cannot incrementally added to the network. And in Hopfield Network, the weight of a synapse depends only on information available to the two neurons it connects. This property is called a local learning rule. But the pseudo-inverse learning rule is not local. The update does not depend on either side of the connection, as it calculates the inverse of the weight matrix. Again, this learning rule is neither local nor incremental. Next, let's implement the code to store and recall MNIST image patterns in a Hopfield network with the pseudo-inverse learning rule. Load the MNIST dataset. This time, let's store 100 MNIST images in a Hopfield network. And we transpose the matrix X to match the matrix multiplication order explained on the previous page. Convert the pixel values of each image pattern into bipolar states, +1 and -1. M is the number of neurons, and N is the number of input patterns. As we saw on the previous page, we compute the pseudo-inverse weight matrix as follows. First, we find the Moore-Penrose pseudo-inverse matrix of the input pattern X. For this, we use the PinV function provided by NumPy's linear algebra module. Then we use this formula to compute the weight matrix W. Fill the main diagonal of the matrix with zeros. Next, we compute the pseudo-inverse matrix of W and fill the main diagonal of the matrix with zeros. Now that we have the 100 MNIST image patterns stored in the pseudo-inverse weight matrix, we can use this matrix to reconstruct the corrupted images as we did in the previous code. The rest of the code is very similar to the previous code, so I will skip explaining it. Let's check the results. You can see that all the corrupted images have been successfully reconstructed. The energy of each image is also significantly reduced. We can see that using the Hebbian learning rule, the Hopfield network could only store 2 MNIST images. But using the pseudo-inverse learning rule, it could successfully store more than 100 image patterns. Let's run this code. We got the following results. In this video, we looked at the pseudo-inverse learning rule. In the next video, we'll look at the Storky learning rule.